Hello everybody, my name is Sam and welcome to Rust Fasttrack episode 5. In today's episode we're going to learn about ownership. Now ownership is one of the ways Rust ensures safety and tries to prevent data races and all of the nice stuff that Rust gives you as security features. Now the core concept of ownership is only one name, only one variable can own a piece of data. So let's demonstrate this real quick. So the easiest way to demonstrate this is to say, what are we on here? AA. Okay, so we'll say let AB equal. We'll use a vec of I32s. They're always good to work with and demonstrate what you're trying to do fairly nicely. Okay. And let's let AC equal AB. Let's do this. So we will print line AB. Yeah. Okay, and we'll try and do it again here. And this should not work correct. Okay, let me show you the compiler real quick. There we go. So if we do cargo build to build it, and you see use of moved value AB. AB moved here because it has type blah, which is moved by default. So it got moved when we said let AC equal AB. So it got moved here, and because it's been moved, it's no longer accessible. The value here is no longer owned by AB, but instead owned by AC. Now, let's say we want to do something like this. So we say AB, AC, AB. Okay, now at present we can't do this because AB here has been moved. Now, a way we can get around this, those of you who have sort of made some conclusions from watching all the previous Rust we've done, would be to stick this in a scope, because then, if you remember back to the Lifetimes episode, AC will die. But let's see what happens here. Let's see what happens if you try and solve this problem like this. We still get the problem. So why do we get this problem? Well, it's still being moved in the same place and we're still trying to use it. So why is it being moved? Well, the problem really here comes down to it doesn't matter that we're moving into a separate scope, because we're still doing this move and AC is still coming to own this data, and when AC goes out of scope, AB isn't this data goes out of scope with it. So the fact that AB is existing up here is irrelevant. Now, a way we can get around this is to, instead of making AC equal AB, we can make it a reference to AB. Now, this means that AC can be treated as if it is this data that's stored in AB, but it doesn't take ownership. Now, this is called a reference. So this is called referencing. So let's rename this ownership and ownership, referencing, and borrowing. Okay, so this is a reference. Now, what this means here is now, in theory, if the compiler is feeling nice to me and I know what I'm talking about, it builds and it runs. It gives us all the same complaints we're used to, but it built, and when we hit run, you can see AB 1234, AC 1234, AB 1234. Now what we can actually do is drop this back into the scope, and the reason for this is, I mean, we're just taking a reference. This bit of data doesn't need to die. Now, if we're not going to use AC anywhere else before the scope ends, it might be wise to embed it in a separate scope so that the data lives for a shorter time and uses less stack memory. But that's a really low-level optimization that you often don't need to do, but sometimes you've got to. So we're saying AC is now a reference to AB, and references are denoted with these ampersands. So if we just try and run this one, so we will just cargo run it, and you'll see we get the same result. So 1234, 1234, 1234. Right, now let's get really unorthodox. So let's say we make AB mutable, which is, we want to be able to change this. and then we're going to say AB is going to gain 5 on the end. We want to update this again. So this should be fine. AB is just referencing this. Should be no problems. And you should see AC grabs the updated value with this push. So let's go ahead and see how this plays out. So we will run. And you see it plays out much how we'd expect. We get 555. Now I'm going to show you something interesting. Let us instead grab that and put it here. Now this is where you can see what AC actually does. So let us go back here and we will do cargo run and we get an error. And that is what makes this so powerful. Now what it says is cannot borrow AB as mutable because it is borrowed as immutable. What this means is when we do this reference here, when we say, okay, yeah, you have access to this, we are taking this as a reference. This is not alterable by AC. But what this means is we're also saying this value in AC isn't going to change unless we shadow it. The value stored in AC is going to be just a single fixed value that is AB. So we can't actually use AB as mutable, or change it, as it were, once we've taken an immutable reference from it. So a way around this is we could take an immutable reference. And this is called a borrow. And so we're going to take a borrow, and we're going to take and mute AB. So now let's run our code. And we got another error. So let's go have a look at that. Cannot borrow AB as mutable more than once at a time. And now you're starting to see where things are complicated. So let's actually load the docs real quick. Doc standard. And what we're going to look at is we're going to look at vec. And vec is obviously the type, that is the vectors. And we are specifically going to look at the push function. And you will see that push takes a mutable reference to self. Now, what this means is, in essence, this bit here, you can think of it almost as saying push and mute AB 5. So you can think of it almost as doing that. And part of the safety guarantees in Rust mean no two things have the power to edit the same piece of data at the same time, because that gives you a data race where two things try and change the same thing simultaneously, and data races cause undefined behavior. And undefined behavior is always bad because it means that you don't know what's going on. And so the Mr. Nasty hacker might find a way to exploit that. So that creates insecure code. So you're saying, okay, but what if I want this effect? I want to be able to take a reference to AC, output it, and then go about my way. Well, this is where bringing back in those scopes is helpful. Because now, that should be outside the scope, AC is going to die here, and with it this mutable reference, which means we no longer need it, but we then lose this ability to print it out here. So that you get this very complicated thing going on that essentially the compiler is stopping you from writing unsafe code. What I'm doing here is fundamentally trying to create unsafe code. I'm trying to have 2 bits of data update with the same thing. And that is really unsafe code. If 2 bits of data can change the same thing at the same time, well, there's a lot of room for things to go wrong there. So fundamentally, good secure code design will not allow you to do what I'm currently doing without a lot of work to make it secure. And the Rust compiler enforces that with ownership. Now, so I've shown you how to do a reference with this and a borrow. Now let's see how they're actually used, because all you've seen me do so far is produce a ton of errors out of the compiler to demonstrate how the compiler is going to force you to write safe code. And to do this, we're going to write a function. Now we're going to write a function called foo. Fairly standard function name. It's not going to return anything, but it's going to take just a value. So it's going to take some value of type t. Actually, no. We're going to make it take. We're going to get onto this in a second. Now, what I'm doing here is I'm saying I want to accept any value of type D, where D is a value that can be printed with the debug argument. So that's this one here. Now, this is called generics and traits implementations, and I'm actually going to talk about that a bit later in this episode. But for now, just trust me that what this does is says accept any value that is debuggable. And then all it's going to do is it's going to print, going to debug print bar followed by the value. So this is sort of, you've just seen a quick glimpse at generics, and I'm going to explain them a lot more in a future episode. But really my point here is I'm going to do this. Foo AB. Right, let's just test that, let's see if that works. So let's go to our command line, and let's run. So we should expect bar followed by that. Use undeclared trait name debug. Give me a sec, let's find out what I'm doing wrong with implementing debug. Oh dear. There we go. Implement debug. What does it not like about my implementation of debug? Use of undeclared trait name debug. What does debug come from? std fmt debug. Okay, so let's just quickly bring that into our code. You need to implement the standard format of debug. Really nice way to think of that. Again, this is generics, we'll get into that more later. I'm just doing that so that I can be kind of extensible with my code for the demo here. So now let's just clear this and run. And you see we get back bar 1, 2, 3, 4, which is what we expect. Right. Now let's do something crazy. Let's try and just print out what this is again. So we're just going to say AB contains this. Okay? So let's have a look at what's in AB. So you probably think, okay, yeah, this will work fine. I see no reasons why this shouldn't work. You may be able to guess by how I'm talking that it's probably not going to work, but let's have a look. Use of moved value AB. And you're thinking, but we didn't move it. We never said let this one name equal this other name, except we did. We're saying val is now going to be this value when we call it here. And so what we're actually doing here is transferring ownership of this vector 1, 2, 3, 4 from this value AB into this value here, val, within the scope of foo. And then when this dies, when this goes out of scope, when val dies at the end of this, when its lifetime expires, that data goes away with it, which means we can't have access to it here. Now, how do we get around that? Well, it's fairly easy. We use a reference, like we spoke about earlier. And now, you're going to see a type complaint. So let's just get that type complaint quickly, so I can demonstrate that I know what I'm on about. And it says, expected a pointer, found a vector. So let's give it the pointer it wants. And so what it actually wants you to do is explicitly say that this is a reference. Now, the reason you do this is that you can read it fairly cleanly and see what is and is not available. So let's have a quick look now. Let's run. And it works. Bar 1, 2, 3, 4, and AB contains 1, 2, 3, 4. So you'll notice that despite the fact that we've accessed this from somewhere else, it's had a different name, because we've used a reference, like we showed earlier, the compiler doesn't get too screwed up with us. Now, let's try and do that crazy thing we did earlier where we want to have some mutability. So we're going to do it the exact same way, where we take a borrow instead of a reference to AB. And in here, what we're actually going to do is then say, well, I've said it, what gives push? So I'm just looking up in vec what supplies push, or if it's just a vector only thing. Push is vector only. Okay, so we're going to make our code less generic. I'm actually only going to accept a vector of type t, where t is anything. I know, which we're going to accept a vector of just I32. We're going to be really, really ungeneric, which means I don't actually need to wrap this anymore in a type declaration, and we can just say vec I32. So we've become more boring and less extensible, but whatever. And we're actually just going to then here say val.push 5. So let's run this code. And you'll notice it did what we wanted it to. It modified the data. Now, you may be thinking, but don't these two things have access to it at once? Well, no, because of the way these lifetimes work. This lifetime expired. And we're no longer trying to access val outside of its own scope, as it were. So this code is actually 100% safe. There's no way two things can edit this at the same time, which is really powerful. And so you've seen now in this code how to do a, what am I talking about? How ownership works. So how we move ownership of AB, this data here, to val down here and inside this lifetime. How we can make it so that we can still use it afterwards and it doesn't get moved by using a reference, and how we can modify data. Now, the things to note here are, let's knock this back to just a reference. Let's make it so that we're not doing this push operation again. Well, now, what happens if we try to say ab.push 5? So you remember we tried to do this before when it was just a sort of embedded scope. So let's try and do this again. And it worked. So you may be thinking, well, why did it work here? Again, it's to do with the lifetimes and the way it called out, and also to do with the way the code was structured before. But I'm just demonstrating how here, even though we've created this reference to it, we're still able to push to it because our reference dies down here at the end of this scope. So this move here, there's no move that happens. We're able to push to it fine, and we're actually able to use a borrowed reference as mutable when we do it in this way. Now, the last thing then is showing mutability in two places at once. So val.push 5, and then let's make this one here 6. And you'll see we get this 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. So this code hopefully does exactly what you would expect. So you now understand the difference between just handing the value over, transferring ownership, taking a reference, and lending it out. Now, you can't lend something out twice like this. That's the thing. You can't have two mutable references coexisting at the same time. So what you can't do is say, and I'm going to drop back down into a single scope here just to demonstrate this, so I'm going to get rid of this. What you cannot say is let mut AC equal a mutable reference to AB. Well, you can say that. That should build fine in theory. Yeah, it builds fine. You cannot then say let AD also be a mutable reference. So now if we try to build this, it's going to fail. So you can have as many references as you like. We can have as many immutable references as our heart desires. We can do this as much as we like. But you can only ever have one mutable reference at a time. Now this is very important when you're dealing with multiple threads. So let's just run this again. And you see that worked fine. So now I've shown you how this works and how ownership transferring works. Let's do something that you probably won't expect. Let's write a function called take. That's just going to take an I32 now. So let's I forget what we're on now. We're still on AB equal 6. And And so now you're going to look at this and you're going to say, okay, well when we call take, this is going to transfer ownership because there's nothing here. So let's just say take AB. And I'm just going to say down here, all we're going to do is we're going to have a quick look at what's in there. So now if we run this, unresolved maybe did you mean value? I did mean value, nice shout. I love when the compiler tells you exactly what you're doing wrong. And you see we get this 6 out at the end. So clearly this has worked. But now if you remember from before, val should now have ownership of AB. AB should no longer be accessible. So I should not be able to say this. And I just used a full stop instead of a comma. But I can. We got 6 twice. Now why is that? Well, this is where I said I'm going to have to teach you traits. So traits are these things you may have seen me reference a bunch. You saw me use debug a second ago. Now traits are Rust ways of implementing things, creating these things called generics. And one of these traits is called copy. Now copy is, what am I looking for? STD marker copy. Well, here you can see it in action. If we have some required structs, basically what copy does is copy types that can be copied by simply copying bits. Now what this means is when all your data is a bunch of bits of memory, you can copy them and get around these move semantics. So you can make it so you don't have to worry about the fact this value has been moved. In fact, this value will never move. It's just going to do a really sort of simple memory copy because it's got this very, very shallow thing. Now, they sort of show it here. If we create some, think of this as making a variable type. So we're going to create some variable type foo. We're going to create an instance of it, x. We're going to make y equal x. And now x has moved into y. So control of foo is now, like x is now controlled by y. So we can't print line x because that's going to give you this use of move value that we've just been seeing. Now if we gave foo copy, well then y is just a copy of x. Y by default is going to copy x instead of moving it. Now this is going to be a little hard to understand, but basically all it means is copy is there for values that are simple. Literally things that are just bits. And here you can see everything copy is implemented for. In theory, it's probably not everything. Yeah, because this doesn't list all the things like... does it? Yeah, it does. So here you can see everything copy is implemented for within the standard library. And basically, if you've created a variable that only uses these, you're pretty safe to use copy, rather than having to sort of work around with these references and these move semantics. And so, yeah, it's fine. Now, when you want to use copy, when you want to implement copy, you're going to do it whenever you think your data can be, which basically means is it only made up of stuff like this? And we'll get onto that at a later date. But basically, anything that implements copy, for which, I mean, okay, yeah, it's defined by the compiler, I guess. But basically, anything that you make implement copy by using this derived copy, you're not going to have to worry about these move semantics on. And so one thing moving into another and then no longer being accessible. And that's why with I32s, because if we go down here, here we go, I32. So for I32, I mean this is I32x4, but I mean it's implement. If we go to I32, you'll see it's implemented there. No, we want this one, the one that's labelled as primitive type, and we want to search implement Why is copy not listed? Well, it is copyable, you just saw it copy. I'm not sure why it's not showing as copyable. But basically, yeah. As long as something can be moved with sort of these simple bits just being shifted around, a lot of the time you're not going to have to worry about dealing with ownership, referencing, borrowing, all of that stuff, because you're going to be able to use copy instead of move. So I'm wondering if this implements onto something generic, like because basically here you might be able to see some of these are actually traits. You can actually implement one trait for another trait and say everything that implements this should also implement this. So I'm wondering if there's something that i32 implements that gives it the ability to do that. I want copy, and here. So let's just check what this implements. This implements a lot of stuff. Is any of that stuff in here? Ordering won't be. Implement ord, which returns ordering, but that's not. Yeah, there's lots of stuff it could be, but basically, all I'm pretty sure this means is that one of the things in here, like one of the things in this list is probably implemented by i32, and that's what gives it the ability to do that. It wouldn't be clone. Clone is different. I'll explain clone in a future episode. Wow, loads of implementations of lots of stuff. Sure. What is sure? Oh, that's shift right. Yeah, all of the mathematical operations are being sort of set up here for i32, so there's remainders, multipliers, but that's how all of this stuff is implemented. So add i32 for i32. This means we're going to set it up so you can add i32s together. And so traits are these really fundamental thing that lets you implement functionality, both compile side functionality, so you can use things like the plus sign, the minus sign to add your custom types together. And also it implements stuff like copy and display and all these traits that I've sort of hinted at a bit that you may have seen. So like debug you saw earlier, and that provided this debugging output type. In fact, I can show you debug. Let's look at debug. All debug requires is you create some format function that returns either a result of either nothing or an error and does stuff. Like, it's pretty simple, but most of the time you just use this derive keyword, which I'll also explain at a later date. This is meant to be an episode on ownership, referencing, and borrowing, but you can't explain those without touching on traits a little bit, simply because of the existence of copy. So hopefully I've not confused you too much by going too far ahead and looking into traits, as there's going to be a long episode in the future on just traits. But for now, hopefully I've now explained ownership, referencing, and borrowing, and that's actually going to conclude our talk about variables. We've spoken about data types, we've spoken about mutability and shadowing, we've spoken about lifetimes, and we've spoken about ownership, referencing, and borrowing. I mean, the only other thing to mention is sort of that tick notation I didn't show you before, but really I think it's just best if you read the Rust book on that, which is my Firefox needs resetting again, there we go. Which is at doc.rustlang.org/books/ that is not how you spell book. And that's got all kinds of information in it, and really, I think just reading the lifetimes page here is going to give you pretty much all the information worth knowing about how they work, and you should now, having watched these first 5 episodes, have enough knowledge to be able to actually read and understand this page. A lot of the stuff in here is really heavy and gets really complicated really fast, and so that's why I'm not actually following on the order in here to teach you things. So things like variable bindings, I've sort of glossed over them. I'll come back to them in a sec. But yeah, the book is invaluable, the docs are invaluable, and hopefully I've explained these move semantics, ownership, referencing, and borrowing, and I've touched on traits enough that you can kind of appreciate what they are a little bit, even if you don't understand